In my previous lectures, I had discussed about the chemistry of S block elements, that is alkali metals and alkaline earth metals. Today, I would like to draw your attention to the chemistry of P block elements. As you all know, main group elements are classified into two categories. One is S block, consists of two groups, and P block consists of 6 groups with regular addition of electrons from P1 to P6. That means group 13, 14, 15, 16, 17 and 18. In the group 13, we have, this is the P block, about 30 elements are there excluding helium, and in the group 13 we have 5 elements are there. Start with boron and aluminum, gallium, indium and thallium, and in the group 14 we have carbon, silicon, germanium, tin and lead, and in group 15 also called nitrogen series, we have nitrogen to begin with, and then we have phosphorus, arsenic, antimony and bismuth. In the group 15 oxygen series, also called chalcogen series, we have oxygen, sulfur, selenium and tellurium, and in the group 17 we have halogens, fluorine, chlorine, bromine and iodine, and lastly we have inert gas elements such as neon, argon, krypton, xenon and radon in group 18 along with helium, and these 30 elements dominate P block chemistry, and let us discuss one group at a time. To begin with, let us start discussing the chemistry of P block elements such as group 13. In the group 13, we have boron, which is typically a non-metallic element with little metallic characteristics, and rest of the metals such as aluminum, gallium, indium and thallium all are metals, and all group 13 elements show little higher ionization energies or ionization enthalpies compared to alkaline earth metals. However, higher ionization energy for removal of 3 electrons is anticipated in case of boron compared to the rest of the elements because of the smaller size. And similarly, there is some the difference in the chemical properties also one can see between boron and rest of the elements, and aluminum has many similarities with beryllium that I discussed while discussing the chemistry of alkaline earth metal elements. For the group 13 elements, group oxygen state is +3, that is a stable oxygen state. Because they have S2P1 electron configuration, all the 3 electrons can be removed to generate a trivalent cation, and hence the group shows +3 as the most stable oxygen state, and stabilization of lower oxygen state for the heaviest elements is not possible, that is only thallium in this case, and +3 state compounds of thallium are highly oxidizing, that means it has a tendency to getting reduced to thallium +1 state to retain those S electron in its place, and this is called inert pair effect, and I would elaborate more about inert pair effect later. However, this inert pair effect is more pronounced among other elements of group 14, 15, 16. In case of group 14, it is tin and lead. In case of group 15, it is bismuth, and in the case of group 16, it is tellurium. These 5 elements have little tendency to unpair the S electrons to promote to p orbital to show the group oxygen state, and whenever such oxidations are possible, those compounds are highly oxidizing in nature. Okay. So, boron is a fairly rare element and abundance is 0.001% by mass in the Earth's crust, that is, it is the 34th most abundant element in the Earth's crust, and it has 2 isotopes. One is 10 boron, this is about 19% abundant, and other one is 11 boron, This is about 81% abundant. Of course, when we look into nucleus, nuclear spin for 10 boron is I equals 3, and in case of 11 boron I equals 3/2. The most common sources of boron are tourmaline, that is boron oxide or borax, that has the composition Na2B4O5 OH 4 times and 8 equivalents of water. This is called tourmaline. There is also another ore mineral called kernite. Its composition is more or less same, but differs in the water of hydration. So, just if you look into this one, they are nothing but hydrated sodium borate hydroxide minerals. It is not very easy to purify boron, and one method that is used for purification or reduction of boron is using magnesium. One can take boron trioxide, pure boron trioxide, and subject it to reduction using magnesium. It gives pure boron along with magnesium oxide. The oxide is made by melting boric acid. One can heat boric acid and to get rid of hydrogen in the and get B2O3, and then high purity boron can also be obtained by thermal decomposition of boron trichloride or boron tribromide, combining with hydrogen and passing through a heated tantalum wire. For example, one can consider boron trichloride or boron tribromide. Along with hydrogen, it has to be passed over a heated tantalum wire. Of course, results are better when the hot wire temperature reaches 1000 degree centigrade. So, boron crystallizes in a variety of forms, all containing icosahedral B12 unit. You can see here, this is one of the borate minerals. This is how it looks. This is how the icosahedron looks like, and I have a model to show you here. And this is icosahedron. It has 12 vertices. You can see here 5 are here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and one axial here, one axial here. So, we have 12 vertices are there, and then we have 5, 10, 15 plus 5, 20 triangular faces are there, and 30 edges are there. That means a icosahedron has 12 vertices, 20 triangular faces, and then 30 edges. So, this is how crystalline boron looks like, and it has several forms. All of them have this icosahedral structure. And you can see other space filling model is shown here. In this one, it shows the arrangement of 12 boron atoms in this icosahedral fashion. Okay. So, aluminum is third most abundant element in the Earth's crust, that is about 8.3%. We know the most abundant one in the Earth's crust is oxygen, next one is silicon, and third one is the aluminum. And the common or most common ore of aluminum is bauxite, and there is one more ore of aluminum, that is called cryolite. This is nothing but hydrated aluminum oxide. So, another ore is called cryolite. This is nothing but hexafluorosodium aluminate, sodium hexafluoroaluminate. Okay. And bauxite contains mainly iron oxides such as Fe2O3, silicon dioxide or silica, and several other impurities. In order to isolate pure aluminum, these impurities must be removed. This is done by a method called Bayer's process. So, in this process, what they do is, initially this bauxite is treated with sodium hydroxide to eliminate sodium silicate and form sodium aluminate. It forms sodium aluminate. Of course, silica also reacts with sodium hydroxide to form sodium silicate. So, bauxite treatment with sodium hydroxide gives these two, which results in the formation of sodium aluminate and sodium silicate. So, iron remains as a solid, and when CO2 is blown through the resulting solution, sodium silicate stays in solution while the aluminum is precipitated out as aluminum hydroxide. So, second step is the blowing carbon dioxide through the, so this sodium aluminate reacts with carbon dioxide to form aluminum hydroxide. Okay. So, the hydroxide can be filtered off, washed and heated to form pure alumina. So, this aluminum hydroxide on heating forms alumina. So, the next stage is the formation of pure alumina from aluminum oxide. So, it is performed by electrolytic method. So, in aqueous solution, aluminum oxide dissociates into ions. They are Al3 plus and AlO3 3 minus. So, in solution in aqueous medium, aluminum oxide dissociates into aluminum 3 plus and aluminum 3 minus, such as Al3 plus and AlO3 3 minus. So, on anode one can anticipate this reaction. Al3 plus 3 electrons are added to give aluminum metal. On cathode, aluminum AlO3 3 minus releases 12 electrons to form again Al2O3, and again this process starts, the dissociation of this one happens again. So, that it continuously it goes until all the aluminum oxide is exhausted, and overall electrolysis process can be represented through this equation. So, this is how aluminum is extracted and purified using Bayer's process starting from bauxite, and electrolysis is necessary as aluminum is very electropositive. These days electrolysis of the hot oxide in a carbon lined steel cell acting as the cathode with carbon anode is used. The metal is obtained by electrolyzing the dry alumina in molten sodium hexafluoroaluminate also. One can also do this electrolysis. Okay. So, next one is gallium. It is normally a byproduct of the manufacture of aluminum. That means, in the bauxite it is present in trace quantities. The purification of bauxite by the Bayer process results in the concentration of gallium in its ratio from 5000 to 300 in the alkaline solution from an aluminum. That means, to start with, the ratio of gallium to aluminum is about 1:5000. On concentration it increases to 300. So, once after the bauxite turns into more and more aluminum oxide through a series of processes that I had described, it leads to the concentration of gallium. So, later electrolysis using mercury electrode is used for the concentrated gallium, and this electrolysis will give sodium gallate. Once gallium is concentrated, electrolysis using a mercury electrode provides a further concentration, and following electrolysis of the resulting sodium gallate using a stainless steel cathode affords liquid gallium metal, because gallium is a low melting element and its melting point is 29.76 degrees centigrade. So, at room temperature it is liquid similar to mercury. So, preparation of very pure gallium requires a number of further processes ending with zone refining to make pure gallium metal, and about zone refining method I would explain when I discuss the chemistry of group 14 elements, and especially while purification of silicon and its ultra purification for semiconductor purposes, one uses a zone refining method. That time I give more information about zone refining technique. Okay. So, the other element is indium. It is also a byproduct of formation of lead and zinc. That means, lead sulphide and zinc sulphide ores do contain a small amount of indium, and indium metal is isolated by the electrolysis of indium salts in water. Further processes are required to make very pure indium for electronic purposes. So, crude thallium is present as a component in flue dust along with several other elements of p block such as arsenic, cadmium, indium, germanium, lead, nickel, selenium, tellurium and zinc, and also in zinc sulphide it is present in very trace amount. Thallium is prepared by dissolving the flue dust in dilute acid such as sulfuric acid and precipitating out lead sulphate, and then it is treated with hydrochloric acid to precipitate thallium chloride, that is thallium monochloride TLCl. Further purification can be achieved by subjecting thallium chloride to electrolysis. Okay. Let us look into the reactivity of boron and aluminum. So, element B or elemental boron combines with oxygen, halogens, sulfur and nitrogen and with many metals. It is resistant to acids and only reacts with molten sodium hydroxide above 500 degrees centigrade. That indicates its inertness at normal circumstances towards acids. Aluminum being very reactive metal, usually made unreactive by a thin coating of aluminum oxide. So, freshly if you see manufactured aluminum on exposure to atmosphere for few days will readily form a thin coating of aluminum oxide, and this is called passivation process. Actually, this passivation process is remarkably helpful in preventing the further corrosion of aluminum. So, that way whenever aluminum is not used, if it forms a thin coating, it is actually good for its life, it should not be disturbed. Only when we have to use it for some purpose, then only this oxide coating can be removed through a proper acid treatment. So, aluminum dissolves in hydrochloric acid to give hexa-aqua aluminum 3 plus ion, and hydrogen gas will be liberated, and in strong hydroxide solutions giving aluminates and hydrogen. For example, if you take aluminum and treat with sodium hydroxide, initially it gives insoluble aluminum hydroxide, but on treatment with excess it forms NaAlOH 4 times with the liberation of hydrogen gas. Similarly, indium reacts with HCl to form indium trichloride. With the liberation of hydrogen gas. Same thing is true in case of thallium. Thallium on treatment with nitric acid, it forms thallium nitrate plus H2 comes out. When boron is heated with most metals, metal borates are formed very similar to carbon and silicon interacting with the metals to give corresponding carbides and selenides. In the same way, so these borides can also be made by heating with metals. Compounds with the different composition can be formed. The structure of these borides are dependent on the metal to boron ratio and contain either single boron atom or a pair of boron atoms or a chain of boron atoms or double chains or sheets or even clusters of boron atoms. For example, compounds with composition say M2B, these are all borides. If the composition is say M2B, so example Fe2B, okay. So you have single boron atoms are there, in the lattice, and while those with 1:1 ratio, for example in FeB, MB, so here have a single chain, boron atom chain, okay. And in MB2, B sheet will be there, boron atom sheet will be there, okay, between the two layers of metal. And in case of MB6, 6 boron atoms arranged in an octahedral fashion, will be there in the lattice. So, here essentially 8 boron atoms make a cube, and at the center this B6 octahedra will be placed, and similar to CS-Cl type structure. In case of MB12, this indicates the type of borides we come across with metals, example aluminum B12. So, here the boron atoms form a network of linked icosahedral clusters similar to free crystalline boron atom. That means, like this boron clusters containing 12 boron atoms will be included in the lattice. I can show you some of those things here. You can see the structure of this one. It is a chain where the ratio is 1:1. You can see here clearly this, the gray ones are the metals, and here boron chain is there like this. Here one can see the ratio, overall ratio or composition will be 1:1. And in this one sheet case, here you can see a metal sheet is there, and below that a boron sheet will be there. So, they are alternately they are arranged in this fashion. And for example, if you just look into zirconium bromide, you can see here the green one is zirconium layer, and the next one beneath that one is boron layer is there, and below that you have again zirconium layer. It continues in this fashion. And in case of borides of the type Mb6, as I mentioned, you can see this cubane consists of metals at 8 corners, and that is encapsulating this boron cluster with boron atoms are arranged in octahedral fashion. So, now let us look into the reactions of boron and aluminum with halides or halogens, and all give trivalent halides. So, that means all combination of all elements of group 13 with all elements of group 17 are possible to generate trivalent halides of the type MEX3, where M is a group 13 element and X is group 17 halogen, and except thallium triiodide. If you just look into thallium triiodide, one is highly oxidizing and one is highly reducing, and it is very difficult to bring two entities which is one is highly oxidizing and one is highly reducing, difficult. As a result, TLI3 thallium triiodide is bit difficult to make, and also it is highly unstable. And all these group 13 element halides can be seen, and among them this BX3 boron halide trihalide is a planar molecule, and it appears like this. You can see here a typical boron trihalide can be represented in this fashion. It is trigonal planar, and in this one one p orbital is left. So, that is perpendicular to the plane. So, it is something like this. We have this, if you assume this is p orbital, this is perpendicular, and of course, this is the p orbital, empty p orbital. So, in case of BF3 and also to an extent in case of BCl3, pi back donation can be anticipated from fluorine, or as they also have filled p orbitals in this fashion. If you recall the Lewis dot structure we wrote, it can be Cl or F. So, here what it is expected is these lone pairs can interact with empty p orbital coming here to have some sort of p pi interaction, through which some of the electrons can move from halides to boron, so that its electron deficiency can be compensated. Okay. And of course, although one can think of this kind of arrangement, it is little less pronounced in case of boron trichlorides, whereas it is more in case of boron trifluoride. As a result, what happens, boron trichloride is more or strong Lewis acid compared to boron trifluoride, despite fluorine is the most electronegative element. For BCl3, overlapping of orbital is poorer, so the boron is more electron deficient. So, that means when we consider fluorine, another thing one should remember is, if you take here fluorine, both are essentially 2p orbital and 2p orbital here. Here overlapping can be more efficient because of the similar size. On the other hand, when you consider chlorine, you are considering 3p orbitals. The 3p orbitals are little larger in size. As a result, what happens? Interaction of 3p orbitals with 2p orbitals are not very efficient. As a result, what happens? Electrons are not readily moved from chlorine to boron atom. As a result, what happens? The electron deficiency still remains intact at boron atom. As a result, BCl3 is much more Lewis acidic in nature compared to boron trifluoride. So, you can see here in the picture, you can see that boron empty p orbital and filled p orbitals of fluorine can be seen, and the size is essentially same. You can anticipate some sort of interactions here, and through which, and also another important aspect one should remember is fluorine being the smaller one, when you have 8 electrons in the F minus, due to the inter-electron repulsion, it has a tendency to reduce its density by giving some electrons towards the boron empty p orbital. As a result, what happens? It carries the multiple bond character, and as a result, what happens? It is less Lewis acidic in nature compared to BCl3. And same thing you can see here in case of BCl3, you can see the size of p orbitals are little larger compared to the boron p orbital. So, here the interaction is not very effective. So, boron atom still has more electron deficiency and making BCl3 much stronger Lewis acid. So, essentially we call this as a mismatch of orbital. For the same reason, when we go to higher elements in the p block, multiple bonding is not possible, and multiple bonding is only effective in case of first row elements, where we involve 2p orbitals for such pi bonding. Okay. So, BX3 or boron trihalides are monomeric in nature, where the structure of aluminum trihalide depends on the type of halides we are considering. Aluminum trifluoride is a high melting polymeric solid built from fluoride bridged AlF6 octahedra. So, here the structure of aluminum trichloride in the solid state has 6 coordinate aluminum centers with chloride bridges. That means, both aluminum trifluoride and aluminum trichloride show octahedral geometry in solid state. However, in the liquid state and also in gas phase, aluminum has a dimeric structure. That means, a dative bond exists between aluminum and chloride in the bridging unit, and aluminum tribromide and aluminum triiodide are dimeric in all states. So, you can see the structure of aluminum trihalides here. If you take aluminum trichloride, one can write, and if you assume aluminum has undergone sp3 hybridization. So, here what we have is S2P1, and they combine together to form 4 sp3 hybrid orbitals having 3 electrons, one is empty, and now 3 sp3 orbitals with 1 electron will interact with chlorine to form 3 AlCl bonds, other one is empty. So, now similarly I can write another one here in a opposite direction. So, now here this lone pair of chlorine can be given here, and this dative bond forms. This stabilizes the structure. As a result, aluminum trichloride will exist as a dimer having Al2Cl6 formula, and you can see that structure given here, and inner angles are about 86 degree and outer angle is 90 degree. It is a aluminum is in a typical tetrahedral arrangement, and also because of dative bond you can see that AlCl bond is little longer, 234 picometer, whereas the terminal bonds are shorter because they are covalent. The distance is 224 picometer. You can also see aluminum fluoride giving a 3-dimensional structure, and here another reason why it goes for tetrameric structure or octahedral structure is very simple. If you just look into the size of aluminum and size of chloride, so the size of fluorine is much smaller compared to the chloride. So, as a result, when fluorine makes an attempt to have a dimeric structure, the angle here does not permit two aluminum atoms to come very close to each other. So, in this case, if both the aluminum come very close to each other, they repel because of both are positively charged. Because of this repulsion, what happens? This bent structure is not possible. If the bent structure is not possible, one can think of a linear structure. If linear structure is there, then dimeric structure is not possible. You can possibly think of a tetrameric structure. This is what exactly happens, and if you just look into each unit in aluminum fluoride in the solid state, you have a tetrameric structure like this is there, and in most of the cases when fluoride reacts with several elements from P block or D block, and always they have a linear structure to keep this angle close to 180, and in those cases obviously you cannot have dimeric structure. It has to be either trimeric or a comfortable strain free tetrameric structure. All the trihalides are powerful Lewis acids forming adducts of the type MX3L. That means, if you take any Lewis base close to trihalides, they readily form adduct of this type. For example, if you take and if you bring ammonia, it readily forms an adduct of this type. Often BF3 is used as an adduct of diethyl ether. So, BF3 is actually sold and also stored in this fashion by making an adduct with diethyl ether. So, the formation of anions of the type MX4 minus is also because of the Lewis acidic properties of boron trihalides of group boron trihalides or trihalides of group 13 elements, and this is essentially nothing but the acid base complex formation. Okay. So, for example, BF3 plus NaF if you take, it forms NaBF4. So, it happens all aluminum and heavier group members are also show a maximum of 6 coordination, and that means in case of boron we can, because of presence of only s and p orbitals, one can think of a maximum coordination of 4, whereas in case of aluminum one can use d orbitals, and aluminum and heavier group 13 elements one can use d orbital to increase its coordination number. As a result, they will show up to a maximum of 6 coordination number. So, we saw now all group 13 elements form trihalides of the type MX3. So, all group 13 elements also form diatomic halides of type MX, okay, with element in +1 oxo state. However, except thallium all are unstable towards disproportionation to the metal and the trivalent halide. Only in case of thallium chloride or thallium halides, +1 state oxidation state is very stable. So, even gaseous thallium chloride, for example, is unstable to disproportionation, and aluminum chloride and gallium chloride can be readily formed by the reaction of aluminum or gallium metal with HCl at high temperature and low pressure, giving red colored aluminum trichloride or gallium trichloride, okay, which are condensed at low temperature of 77 Kelvin. Okay. So, on warming, these undergo disproportionation to form the corresponding trihalides of this type. So, that means this is called disproportionation reaction. +1 is giving +3 and 0 valent metal. In case of boron trichloride, when it is treated with mercury, it is reduced to B2Cl4, that is +2 state boron dichloride with the formation of mercury chloride. One can also use copper atoms instead of mercury here. So, some atoms of the same element are oxidized and some other reduced in the same reaction can be described as the disproportionation reaction. For example, in case of this one I showed you here. So, this one since it is unstable, it readily undergoes disproportionation to form MCl3 plus 2M. So, reverse of this reaction is called conproportionation reaction. That means, the reversing of disproportionation reaction is called conproportionation reaction. That means, when MCl3 is treated with excess of 2M, it gives 3 MCl. So, opposite reaction is called conproportionation reaction. Okay. And B2Cl4 decomposes at room temperature to form progressively B8Cl8. So, that means, except for trivalent boron trihalide, others are unstable, and B2Cl4 even at room temperature it dissociates or decomposes to give higher series halides such as B8Cl8, B9Cl9, and also higher clusters such as B10Cl10, B11Cl11 and up to B12Cl12. So, in case of B12Cl12, boron retains icosahedral structure with each boron having one chlorine atom, and gallium 2 occurs in the species. So, in this species anionic halide Ga2X6, gallium is in +2 state, and here where X equals Cl, bromine or iodine, okay, formed by electrolysis of gallium metal in strong acid, and these essentially contain gallium-gallium bond, and that accounts for oxidation state of +2, but are readily oxidized by halogens. On addition of halogens, they readily form GaX4 minus, very similar to AlCl4 minus or BF4 minus. Okay. So, let us look into the interaction of boron with hydrogen. Boron forms more hydrates than any other element in group 13 series, and these essentially electron deficient compounds have both 2 centered 2 electron and 3 centered 2 electron bonds. These compounds can be classified into 2 groups having BNH N plus 4 series. Is one type of boron hydrides. Another one is Bn Hn plus 6 series. The simplest boron hydride is BH3, and this is never been isolated, and this one has a tendency to undergo dimerization to form B2H6, and that means the smallest boron hydride is diborane or B2H6 formed by the reduction of boron trifluoride with lithium aluminum hydride. One can conveniently prepare by treating boron trifluoride with lithium aluminum hydride. The simplest borane is diborane, and higher boron hydrides can contain the same structural features as B2H6, that means 3 centered 2 electron or 2 centered 2 electron bonds with one or more boron to boron bonds, and these higher boron hydrides can be prepared starting from diborane itself. For example, when diborane is heated to 100 to 120 degree centigrade, it forms B4H10 and H2 is liberated. Similarly, when diborane is heated to about 180 to 220 degree centigrade, it forms B5H9 plus 6 H2. And one can see here the diborane structure is shown here, and it is very easy to understand the 3 centered 2 electron or electron deficient bonds. We can again use valence bond theory here. If we take BH3 to start with, to the formation of BH3, one can look for again hybridization of S and P. So, this one essentially what happens before the bond formation, they are distributed in this fashion. So, that means S electron is promoted to P. To have a situation like this, we have now 4 sp3 orbitals, one electron, one electron, one electron, here no electron. So, now BH3 what it does is 1s electron of 3 hydrogen will utilize these 3 sp3 hybrid orbitals to form 3 BH covalent bonds, and now one of the empty orbitals will be like here, and similarly one can write for another one in this fashion. Now, essentially this interacts with this one and here this one to form a diborane. So, here 2 electrons are there, here 2 electrons are there, here no electron is there, here no electron is there. So, now if you overall count the electrons present between B, H and B, it is 3 centers are there and 2 electrons are there, and same thing is true in this case, whereas here we have 2 electrons, no issues. So, we have one 3 centered bond here and another one 3 centered 2 electron bond here. So, that means in this one we have a total of 2 3 centered 2 electron bonds and 1 2 3 4 4 2 centered 2 electron bonds. So, this is how diborane can be explained. So, here essentially 2 electrons are delocalized between these 3 atoms to form a 3 center 2 electron bond. This is also referred to as banana bond. So, boron hydrides you can see the structure I have shown here. So, boron, the sp3 orbitals of boron, here this one I have shown as empty, red one is empty, and here 1 electron is there, and here 1 electron is coming from hydrogen, and this is empty. So, total we have 2 electrons here and 3 centers are there. So, this is how the bonding can be explained using valence bond theory in case of boron hydride, especially B2H6. Okay. And other boron series, as I mentioned, you can see we have 2 series, BnHn plus 4 series and BnHn plus 6 series. They give very interesting structural types, and all these structural types can be explained using Wade's rule. At appropriate juncture, I would introduce Wade's rule to explain the bonding and geometry in case of boron hydrides. And for example, you can see here I have shown the structures for 2 higher boron hydrides. One is B4H10 and one is B4H9. Here you can see we have 1, 2, 3, 4, 5, 6 terminal BH bonds, and 1, 2, 3, 4 bridging BH are there. So, overall it is B4H10. In this case, it appears like a square pyramidal structure. That means, probably from an octahedral structure, 1 axial boron atom is taken out, and hence it appears like a square pyramidal structure having 9 hydrogen atoms. In this fashion, we have 4 bridging hydrogen atoms and 5 terminal hydrogen atoms sitting on 1 boron atom each. So, I stop at this stage today, and I would discuss tomorrow in my next class about some reactions of boron hydrides.